the easiest approximation that we can use, and then we introduce the interaction and compare the spectra that we obtain later. Okay, the Turbo-Davidson use the Casida-Davidson algorithm that you represented this morning, and okay, no, go on. This is the Turbo-Davidson the Davidson-Casida equation that you represent this morning. And first of all, this is in red is the interaction term. So first of all, we neglect this part to compute the spectra. Okay. In the independent particle approximation, this is the simplest approximation that you can use. The energy of excitation is the difference between eigenvalues from the virtual state and the occupied state. And the intensity of the excitation is the transition probability. This is presented here in the middle of the slide. Okay, first of all, we have to start from the ground state. So we have to compute the ground state for our molecule. In this example, we compute the spectra of benzene. Okay, this here you can see the PW input, but I think in this week, in the last week, you now able to run the PW. So move on the terminal to example 1. Here you can see the PW input. This is to compute the ground state. Turbo-Davidson input, to run Turbo-Davidson and solve the linear response. Turbo spectrum input. This is the post-processing compute to compute the spectrum in the final, and also you have here the plot script to plot the spectrum with new plot. Now we can check the input of PW. Okay, here you can see the atomic position for the benzene. I think you now know everything about this type of input. Here you can see the number of bands that compute. The Turbo-Davidson needs some virtual states, indifferent with the turbo Langsos that don't need the virtual states. So now compute on HPC in remote, run in remote this PW in remote. So remote npRun PW .x minus in PW. So, no, maybe yeah, okay. In this, I think is already done because the PW is yep, already done. Okay, here I open also page in but doesn't work, I don't know. Maybe it's okay. Sync the output from HPC. Okay. Now, if we check the output of LCF, okay, only 3 seconds. Okay, converge in 10 iteration. Here you can see the energy, the total energy. So okay, the output is converged. Now from here we can move on turbo. So here, okay. Okay, now we have the output of the PW. So we have the ground state in the output and converge. You can see the highest the highest occupied and the lowest unoccupied level. So in an electron volt in EV, here you see the HOMO state and the LUMO state. Okay, in the independent particle approximation, like so before, the energy of the excitation is the difference of the eigenvalues. So the energy gap is the difference between LUMO and HOMO. So in this case, 5.1 eV. Okay, now go to run Turbo Davidson with the independent particle approximation. Now check the Turbo Davidson input. Okay, this flag, if the FT spectrum equal true, in default is false. When you put true, activate, switch on the independent particle approximation. Now we can we run with the independent particle approximation. This is an obsolete variable for this case. In the next version, you didn't use this variable. Okay, this is not important for now. Now go to run the Turbo Davidson. So we can do the same. Remote run. Now we use Turbo Davidson.x. In with the independent particle approximation, this computer is very fast, so I think it is already done. Now maybe I haven't updated the no check. Maybe I haven't. Yeah, I'm wrong, sorry. I already introduced I didn't ever sync the turbo Davidson input, so I already run with the interaction part, so maybe I have to maybe it's already finished because it's not. Sorry. Yeah, because take 2 minutes with the interaction. Maybe I can do a remote. Okay, it's finished. So sorry, I re-update. Okay, now maybe use update. Oh, maybe I'm wrong something. Again. Okay, I'm uh, okay. I don't know how to change the input file in a.
Oscar, but can you edit directly on the cluster the input file?
Yeah, I can edit here. No. I because in the I tested the. No, maybe. Okay, now I update on the cluster there. I have to update the file. So okay. Now take the output from. Okay. this is the output of Turbo Davidson. So you can see it's very fast with the independent particle approximation. And here you can see the couple of excitation with the number of occupied state and number of the virtual state. This is the difference of energy of the eigenvalue. This is the Rydberg energy. And this is the state that the Turbo Davidson compute. Now go to compute the, oh no, now go to the post-processing steps. So we have to use Turbo Spectrum to compute the spectrum of benzene from this file. You can the Turbo Davidson create also the eigenvalue file that you can see in the close this one. You can see in the HPC, you can see the file that the Turbo Davidson create. Turbo Davidson create this output and the eigenvalues file. This you have the difference, okay, of the energy in Rydberg. So go to see the Turbo Spectrum file. You can see also this prefix out here is the same for quantum expression for PW. This here you can see that the method that you have to use to compute the spectrum. You can use Davidson, Langsos, and so on. Maybe check from the okay. Here, start and end, you can see the energy of the spectrum that you want to plot. The increment is the distance from point by point that you can plot the spectrum, the frequency. Epsilon is the Lorentzian broadening because you plot the spectrum. The Turbo Davidson compute a root spectrum, but you can broadening the root spectrum with the Lorentzian, and the epsilon is the broadening of this Lorentzian, and this is the file that you where Turbo Spectrum take the eigenvalues. Okay, run the Turbo Spectrum maybe before I update the file on HPC. Turbo Spectrum you can run also in your lab because it's very fast, but to don't take everything from the HPC and run on the cluster. Okay. Now use Turbo Spectrum.x. If I can open another to this. Okay, now the turbo spectrum create an output. Okay. Here is only read the file, and it's okay. It print some error if there are some error, and also this file that contains the data you can use to plot the spectrum. This is the spectrum. You can see you have the energy and the intensity of the spectrum. So you can plot this, and this is the three components of the spectrum. Okay, now take this file from the cluster. I'll take from HPC. Okay. Now, okay, and now we can use this file to use the plot skeleton to plot the spectrum with the GNU plot. So, open GNU plot. Dot, I don't remember. Spectrum. Okay, the GNU plot created this file. And so here you can see the spectrum. Now check it. Okay, you can see the energy of the first excitation at 5.1 eV. The same difference that we can see from the PW output. If you want to see the script of GNU plot, you can change more stuff from X range, Y range, and so on. This is the X, the label of X and Y axis, and the titles. But this is GNU plot stuff. Now, this is the independent particle approximation. Now move on to switch on the interaction. So we have to modify the turbo direction.x input. We introduce all of this stuff. So first of all, put false if the FT spectrum. So now switch on the interaction. Num end is the number of eigenvalues that we compute. How Iurii said before this morning, Casida formulation is good to extract a few number of roots. So if you increase this number, the computer, the the calculation increase the expensive become very expensive to extract more and more roots. This is the number of the initial vector. This num init, the default is double of the eigenvalues that you compute. This is the maximum number of bases for the sub-bases. So is to use to check the memory that Turbo Davidson use for compute this calculation. This is the convergent threshold. This is the minimum and maximum values of frequency that you can plot in spectrum. Is similar to the, also the name is identical to the turbo spectrum flags. So start finish step, epsilon become broadening, and reference is the value you can expect the peak, so you can extract the 15 eigenvalues near to this value. Okay, now go to modify the input, the Turbo Davidson input. I take from a read file. You can take all stuff here to Turbo Davidson. Right. Past here. Okay. So okay. Num init is the same. Okay. So it is not necessary rerun PW. If you save the TMPD from PW, you can use the same. So now I have updated the Turbo Davidson input. So I sync to HPC. Okay, and now remote MPI run. Okay. Okay, now I have to wait 2 minutes. If there are some questions, maybe we can use this time.
Oscar, there is a question on YouTube.
Oh, okay.
Do you want me to read it?
Yeah.
So the question is, any particular criteria or limits for a number of eigenvalues to be calculated in step 1 apart from computational cost?
For with the independent particles approximation or with the interaction, because I think depend on the system, the number of eigenvalues that you can compute with the turbo Dielectric. So more large is your system, more expensive is extract a number of eigenvalues that you need, because maybe in benzene the first excitation is also the highest intensity excitation in this case, but in other case maybe you have to extract 30 excitation with a little intensity, and maybe the 31 is the highest intensity. So depend on from for the system, the how many eigenvalues you have to extract. So in the independent particles approximation, it's very economic extract a lot of number of eigenvalues, but yeah.
Oscar, there is another question in the chat of Zoom.
Okay.
So it's written, I think the reference tag was missing in the modified input file. Does it matter? Will it find the peaks anyway in this case?
In this case, is not, don't change, don't worry, because, okay, in this case, I extracted the lowest, the lowest excitation. So in this case, it's not necessary.
Yeah, so if you don't specify a reference, it means it's 0 by default.
Yeah.
So
take the lowest
yeah.
excitation. Okay, finish. So I take from the HPC the output. So you can see the difference. No. Okay. Okay, now take 2 minutes. No? So the difference between independent particles approximation 2 seconds to with the interaction 2 minutes. So you understand the difference. Okay, here you can see also every excitation, every 15 excitation. I want to show you the so here you can see the convergence iteration, and there is an iteration. So okay, so the Davidson diagonalization is finished in 29 steps. The current basis set is 42, then the total basis that build in this run is 3061. Okay, and then you can see every 15 excitation. So now go to modify the turbo spectrum. The turbo spectrum input, because also we have to, yeah, I have here. If you check, before the turbo Davison create a benzene DFT file, no? So because we have to set true if DFT spectrum, no? Now create only benzene dot eigenvalues file. So we have to modify the turbo spectrum and say it read this file, not this one. Okay. So we have to delete this, and I think so. To think. Okay. We run turbo spectrum. And create now this one, green plot. Okay, so copy from HPC the dot file. Okay, now I have the that file to plot with the GNU plot, but we have to modify also the script of GNU plot. We have to introduce this. We have to modify the last line of script for GNU plot. So I have plot. Okay, and then it's better reduce the highest value for Y range because the intensity is lower, so you can see the peak with 100 for Y. GNU plot. It's a little bit, so maybe we can reduce more the Y range. Okay, you can see that here the blue peak with the interaction. The red one is independent particles and approximation, and blue one is with interaction in compute with the interaction terms. Okay, so go on. Okay, you see Also the shift, the blue shift, and decrease of the intensity of the intensity of this peak. Now, a little bit later, so I move on faster, I think. Okay, now we move to the example 2 with we use Turbo Langsos program that Iurii before said before this morning. Turbo Langsos doesn't need the empty state, and to compute the spectrum, and also we compute all spectrum one a single calculation. This is the equation that Iurii presented this morning, so I'm leaving this step. Go to directly in the example. So first of all, everything we have to compute the PW. Now there isn't NBND flag in the PW input because we didn't need the virtual states. So we compute only occupied states. Okay, move on to yeah, close this one. Okay, to example 2. If you check, there isn't NBND flags. So run. Yeah, run. Okay. Okay. The second step after run PW is run Turbo Langsos program. This is the input of the Turbo Langsos input. So you can see this LR input is the same for Turbo Dexon and the other code with the prefix out there. This too is important. This is the restart step. This is 100. Every 100 iteration, the code print a restart. So if something the program kill after 250 iteration, you have saved 200 iterations. So you haven't lost everything. Okay, so every 100 iteration, the program print a restart file, and this restart files is when you want to restart from an older file, you can put true and restart from the last iteration that you compute. In the layer control, the itermax is the number of Langsos iteration that you compute now, and EPFL is the polarization direction. So you can, in this case, we compute X direction, but also with 2 is the Y direction and 3 is Z direction. So go. Let's see, this is the same. So go to run. Maybe I think it's already finished the PW. Yeah. Okay. Now go to run the Turbo Langsos. Yeah. Okay. The Turbo Langsos code. So remote MPI run Turbo Langsos X turbo Langsos. So also this step takes a few minutes, I think. Okay, but I can show you from the I can show you the output. This you can see every every Langsos iteration. So for every iteration, print an alpha coefficient is the diagonal one that Iurii show you is is 0. You know, this is the diagonal. This is the beta and gamma. So this is the three diagonal, the coefficient of the three diagonal matrix. So you can see every iteration, turbo Langsos print alpha, beta, and gamma, and this is Z. So this is for the to compute the spectrum. So now the turbo spectrum read this coefficient and compute the spectrum. So maybe the job is done. So compute 500 iteration of for benzene. Now, okay. Now go to turbo spectrum. Okay. Spectrum. Okay. Okay. We can see prefix and now they're the same of before. Okay. This is ether max 0 is the number of excitation that you use to compute the spectrum. So we compute 500 iteration. Here we put 500 iteration, but also you can put a less of, but not more than an iteration that you compute. Intermax is another number for the iteration. In this case, is the same of the intermax 0 because we now don't use the extrapolation, but then we introduce the extrapolation, so these values can increase. Epsilon is the same for the turbo Davidson, so it's the broadening of the Lorentzian. Start and end is the value of the range of the spectrum that you compute. The increment is difference point by point for the spectrum, and the pole is the direction that you compute. So we computed the x direction, so here you have to put the x direction. If you put 2 or 3, the calculation crash, compare an error. Okay, run this turbo spectrum. Okay, Also, in this case, turbo spectrum create the turbo spectrum output to show error or something. And this file dot that. So we copy from HPC this file and plot with the GNU plot. Okay. Okay, so we can check the plot spectrum. So you can see the X range, the benzene. This is the file that I read. Okay, so okay, this is the spectrum that we compute with 500 iteration. You can see we have all spectrum with one calculation. So this is the pro of the turbo Langsos. You compute all spectrum by one computation. Now we had extract only 500 iterations. There are possible that you this is okay, then that I said before, IterMax is 500, so you have to use IterMax 0 500, and this is without extrapolation. Also, you can compute more iterations, so from 500 to 1000 to 1500. Maybe you can try alone this because the time is not okay for me, but important thing, you use restart true. So now you have computer 500 iteration. So if you put here true, restart equal true, the compute start from 500, not from 0. So you can put here 1000 or 1500, restart true, so compute from 501 to 1000 to 1500 iteration. Okay, and here you can see the difference from 500 to 1000 to 1500 iteration. Okay, that like Iurii showed before in this morning, this spectra is not really converged. So you can see the spike, no, the peak, very with very spike. So this is not converged. So you can compute more and more interaction until the convergence of the spectrum, or you can use a trick for turbo Langsos. Now here you can see the coefficient Langsos that I showed before in the output of Langsos. No, every iteration you have alpha, beta, and gamma coefficient of the tri-diagonal matrix. Here is the plot of the beta coefficient. You can see beta, okay, here. There are two different types. This is the odd one and this is the even one. So you can see the coefficient is around of the half of the kinetic energy. at all. Can put 30 around 50 Rydberg, okay, in this case. But you can see that coefficient after a start point, we can see is change more, then is almost the same, no? Is almost a plateau, no? So we can use an extrapolation method to increase the number of coefficient without to compute this coefficient. So we compute a certain number of coefficients. This is the three diagonal matrix that we compute. Now I compute 500 coefficients, no? And we use the extrapolation to increase the number of the number of coefficients. The coefficient that we extrapolate is the average of the beta and gamma coefficient that I compute. So more coefficient you can compute, more good is the coefficient that you can extrapolate. So, but with the increase of the number of the coefficient, the spectrum converge faster. So you can, this trick is very good to obtain the converged spectrum without compute every a thousand and thousand of number of coefficient. Now we can try to use the extrapolation. And this is everything a post-processing step, so it's very, it is not expensive, no? That is almost cost zero, no? We now move to put here 20,000. Okay, and this is extrapolation that we use. Now async turbo spectrum. Okay, so now, okay, now take the new plot and go to see the spectrum. Okay, this is the spectrum with extrapolation. So you can see is totally different from before. Okay, this now down here, but you can see the real difference from the last one. I didn't hear, but maybe in the PDF is so you can see here the spectrum with the extrapolation. So you can see here in red the 500 iteration with extrapolation that I compute, and then 1000 iteration with extrapolation and 1500 iteration with extrapolation. And you can see the conversion from the spectrum. So the extrapolation is a powerful tool to arrive to the convergent spectrum without extract many coefficients from the turbo Langsos. Okay, I'm a little bit later. This if there are some questions for this pattern before I leave it to Iurii, the second part.
So there are some questions on Slack and on YouTube, but most of them are answered. I think there are no open questions.
Yes.
But if someone has some questions, please, you can raise your hand. Okay, maybe if not, we can move on.
Okay, thank you. And if you want to add me to create for me a breakout room, so maybe I can help the tutors to, I don't know. Okay, see you.
Thank you very much, Oscar.
Stop there.
Thank you, Oscar. Thank you very much.
Hello again to everybody. Okay, so we did a half of the hands-on. Now we are going to do the second half of the hands-on. I showed this slide from the lecture just to summarize the first half with Oscar. So now you just saw how to use turbo Langsos and turbo Davidson to compute optical absorption spectra in molecules using these two methods at the bottom, Liouville-Langsos method and Cassida-Davidson. In the second part, we will study solids instead of molecules, so no molecules any longer. So we study solids and we study different spectroscopy, which is electron and energy loss. And we will do that using two methods. First one is Liouville-Langsos again. So this is very powerful, can be used for molecules, solids, and different spectroscopies. And second one, the Steinheimer method, which was not discussed by Oscar so far. Okay, so let me switch to another slides. We have two remaining exercises. First one using the turbo yields code with the Langsos algorithm for silicon, and then again turbo yields code with the Steinheimer algorithm, and again for silicon. By the way, Steinheimer algorithm was implemented by Oscar. Okay, this is the recap from the lecture. Maybe we can skip it in the interest of time. Just in red box, we highlight interaction terms, which are included. We don't do approximation, independent particle approximation that Oscar showed for molecules. So we directly go to the complicated, fully interacting case. So red term is included, and green we highlight the perturbation, which is in this case is the beam of electrons. So we irradiate the chunk of silicon by electrons, beam of electrons. While Oscar was discussing, you take a molecule and you shed light on your molecule. So it's different things. What we want to compute using the turbo yields code is chi of Q and omega, which is the susceptibility. Because when we compute chi, we take the imaginary part multiplied by this normalization factor, and we obtain the minus imaginary part of epsilon minus 1, which is the inverse dielectric function, which can be directly compared with what experimentalists measure. Okay, so we use a Langsos algorithm. The PW input for silicon, you are already experts with the input files for the pw.x code. We will use a quite dense k-point grid, shifted 10 by 10 by 10, and 1, 1, 1, which means it's shifted. And after running the PW calculation, we run the turbo yields calculation. Let me describe immediately the input for the turbo yields code. This input looks quite similar to the one Oscar just showed for, again, using the turbo Langsos code. We have prefix output directory, which is the same as in PW. Restart keywords the same, you just learn how to use them. Now in LR control name list, there are a few things which are new. So we still have this iter_max variable, which is the number of Langsos iterations as before. So, and we also do 500 iterations. There is a new keyword which is called calculator. It can have two values. One is Langsos, which means we use Langsos algorithm. And second, Steinheimer, we use Steinheimer algorithm. So now we use Langsos, and another three variables are Q1, Q2, Q3, which are the three components of the Q vector. I recall that the Q vector is the so-called transferred momentum, because when an electron is scattered in a chunk of silicon, this electron loses energy and it loses the momentum. So Q is the amount of the momentum which was lost due to the inelastic scattering. And so we have three components in Cartesian coordinates in units 2 pi over 8. So let's discuss in more detail how to specify the Q vector. It's on the next slide. So Q vector, bold Q, is has three components, Q1, Q2, Q3, and it's in units of 2 pi divided by A0, where A0 is the lattice parameter. In the case of silicon, this is controlled by cell DM1, which is 10.26 Bohr. For example, let's say we want to, we find some paper in the literature where some people computed electron energy loss spectrum for silicon. They show the spectrum and they write that modulus of Q is 0.53 Bohr to the power minus 1, and they say that Q is along 100 direction in the Brillouin zone. We say, okay, I want to do the same calculation, so how do I specify it in turbo yields code? So we do it the following way. We remember the formula on the top, and we know that the modulus of Q is 0.53. Since it's along 100 direction, we know that Q2 is 0 and Q3 is 0. So only Q1 is non-zero. So we know the modulus of Q, we know A0, and we can compute Q1, which is easy. So Q1 is modulus of Q multiplied by A0 divided by 2 pi. If we do the math, we obtain 0.866. So this is why in the input we have 0.866, 0, and 0. Okay, and this is the third step. Okay, let me describe the third step and we do the calculation. The third step is the post-processing step using the turbospectrum.x program, which Oscar already discussed before. We have, as usual, prefix and output directory. We need to activate the keyword else equals to true to tell to this program that we are using now turbo else code, not turbo Langsos. So the code will be aware that we are using else spectroscopy. So it will do some read of temporary files properly. We have iter_max 0 and iter_max that Oscar described. We can use the same extrapolation technique or not, as Oscar described. For the time being, let's say we don't use extrapolation. So iter_max 0 and iter_max are 500. Why 500? Because in the turbo EELS, it was also 500. So we keep the same number. And then we have broadening epsilon 0.035 Rydberg. Units can be different units, Rydberg, electron volts. We use one which corresponds to electron volts for the energy energy spectrum plot. And we say start for the energy end and increment step, also in electron volts. Okay, so now let's do these 3 steps. So we go to example 3, and we do calculations using cluster to make it faster. Type remote mpi run pw.x, read the input. Okay, we use 20 cores. Oops. Let's monitor the execution of the program. Okay, it's finished. It was fast. This is good. Now let's run the second step using the turbo EELS program. So we type remote mpi run, the name of the program, which is turbo_EELS.x, and read the input turbo EELS for silicon. Again, let's monitor the execution of the program. Okay, it's running. It should take maybe a few minutes. We need to wait. Okay, let's make it do its job. And while waiting, I hope I'm not too fast. Okay, let's while waiting, let me comment on what we are going to obtain. So after these 3 steps, we will obtain a file containing information about inverse dielectric function epsilon to the power -1 at a fixed q point, q vector or q point, because q is fixed, and it will be the function of frequency omega. Of course, this is a complex object. It's not a real function, it's a complex function. So we can evaluate the real and imaginary part of this function using these formulas. And from the knowledge of the real and imaginary part of epsilon -1, we can obtain also real and imaginary part of epsilon. So epsilon -1 is the macroscopic inverse dielectric function. So to compute epsilon, we just take 1 divided by epsilon -1. So these are macroscopic functions, and local field effects are included in the calculation. So instead, if it was microscopic matrix, so 1 over epsilon -1 would mean that we are neglecting local field effects. But in this case, we are already computed fully epsilon -1 and it's macroscopic. Then we can divide 1 over epsilon -1, gives us epsilon. So the file that we obtain from turbo EELS will have information about real and imaginary of epsilon -1 and also real and imaginary parts of epsilon, which we can plot. Without extrapolation, we should obtain this figure. So on the y-axis, we have intensity of the spectrum, of the EELS spectrum, and on the x-axis, we have energy. And we see there are wiggles because the spectrum is not yet converged. So let's see how the calculation is running and if we manage to obtain the same figure. Okay, it's running. I think it should take maybe 5 minutes. So let's wait. Meanwhile, we can answer some questions if there are any. You can also ask questions from previous exercises explained by Oscar. So now we will do just one calculation with 500 iterations. It takes some time, but since we don't have time to do convergence tests by increasing number of iterations to 1000, 1500, etc. So you can do that when we finish the hands-on, and if you have problems, you can ask questions on Slack. And as explained in the README file for this example 3, it's discussed what you have to do. So in the point 5, it's written that you need to compute the yield spectrum without extrapolation. So extrapolation equals no for 500 up to 1500 with step 250 and compare them on one figure. And then do the same steps, but this time using extrapolation technique. Extrapolation equal OSC, which is by constant extrapolation. You can use the restart keyword, as Oscar explained, to speed up the convergence tests, not start from 0 each time. And a second note that when you do these convergence studies, you need to change the name of the output file. So here it's written, change the name of the input file, but actually you better not to do it because we use clusters, so there are scripts. So in order to avoid problems, don't change the name of the input, but change the name of the output files. And then once you have these convergence tests, you are asked the question, which conclusion can you make by comparing the results? So this is what you can do when you have some time. Okay, we can see that the calculation is finished. And now we need to do the third step, the post-processing step using the Turbo Spectrum program. So let's do that. We type remote MPI run. The name of the program, which is Turbo Spectrum. .x, and read the input, which is Turbo Spectrum .silicon.in. Okay, this should take just a few seconds because if turbo yields takes, let's say, 5 minutes, this takes 5 seconds. And indeed, it's finished. Okay, now it's time to copy files from the cluster to the local machine. But on the cluster, if we connect to the cluster, we see that the program produced temporary directory locally. I mean, in this example, we do it this way, which has many files which we don't want to copy. We have output files for turbo yields, turbo spectrum, but we are interested actually in this file which was generated, which we won't just copy this file. Because this file contains information about real and imaginary part of epsilon and epsilon minus 1. So let's remember this name and copy this to our local machine. So we just type rsync from HPC and the name of the file, which is silicon.plot_eps.dat. Okay, the file is here. Let's inspect it. Open the file. And we see a lot of information which was computed by the Turbo EOS program. There are 5 columns. The first column is the h bar omega, the energy in electron volts. Second column is the real part of 1 over epsilon. Third column is the minus imaginary part of 1 over epsilon. And last 2 columns are real part and imaginary part of epsilon, which I just shown on the slide. So we want to plot the ILS spectrum. So we just need the first column and the third column. So this is done by the script, the GNU plot script, which is plot spectrum. So you see this script plots the first column and the third column. So third column is a function of the first column. Okay, so now it's time to execute it. GNU plot spectrum. This produces the file silicon spectrum EPS. We can visualize it. Okay, so this is the spectrum, electron angular spectrum of bulk silicon at 500 iterations without extrapolation. If you have any problems obtaining this spectrum, please let us know. So this was done with 500 iterations, and you need to do it with up to 1,500 in a step of 700 or within step of 250 iterations. And I recall you should use a restart option in order to save time. But what you can see, interestingly, that the spectrum converges when you decrease the number of iterations. You see at 500 iterations, there are unphysical oscillations. You cannot compare this to the experiment. But now when you have more and more iterations, it gets smoother and smoother. And at the end of the day, with 1,500 iterations, you have a very nice, smooth, clean ILS spectrum of bulk silicon, which you can compare with experiments. And remember that this was computed at a fixed k-point mesh, which is 10 by 10 by 10, shifted 1, 1, 1. So we need to also converge the spectrum with respect to the k-points. This is one of the next tasks. Yes, as I said before, to speed up the convergence, as we know already, we can use extrapolation technique. In this case, we can extrapolate, let's say, up to 20,000 iterations. But you can take any other number, 30,000, 50,000. Of course, the more the better, and it doesn't really influence the cost, computation cost. Since calculation is very fast, it's a matter of seconds. You can use a large number, but of course, there is no point going to crazy numbers like 1 million or something, or the order of tens of thousands should be sufficient. And as you can see, if we repeat the same step from 500 to 1,500, but this time with extrapolation to 20,000, and you see that nicely already at 500 iterations, we are converged essentially, almost. It's almost identical to the black curve. So you can see really that in your real life studies and applications, you should always use extrapolation technique because it allows you to compute spectrum at a lower computational cost. And you can verify that this is true by doing this exercise when you have some more time. Okay, this is just a comment that Turbo ILS code gives you not only the ILS spectrum, which is red spectrum with the maximum corresponding to the plasmon. I remind that plasmon is the quasi-particle, and plasmons are actually collective excitations of electrons. So when you excite your system by beam of electrons, the electrons of silicon are excited collectively. It's not their individual excitations, but they're really feeling each other and excited collectively. And if you quantize this collective excitation, the quantum of this excitation is called plasmon. It's a quasi-particle. And on this figure, we plot also other quantities like real part and imaginary part of epsilon. So the real part is green one. You see it can even have negative values. And imaginary part is this purple spectrum. So it is useful to plot also the real part of epsilon. Why? Because this helps us to identify where is the plasmon. So the definition of the plasmon is that the peak in the red spectrum occurs at the energy where real part of epsilon is 0 and the slope is positive. So we have 0, but we go from the negative value to the positive value. So this happens around 16 eV, and the plasmon is around 21 eV. So you see, it's not really exactly the same energy. This is because of the broadening effects. So, but more or less, we can identify that actually this intense peak is the plasmon. Okay. And by the way, just to comment, when there is also real epsilon is 0, but with a negative slope, it goes from positive to negative, you find peaks in imaginary epsilon. Okay, and now we have the last example. Now we have just little time left. So we have example 4, which is the most complex example of the whole school. This is so because the implementation of the Steinheimer algorithm is very recent. As I said, Oscar implemented it, I think it was last year or 1 year or more. So this is recent, and of course, it's not yet perfect, and there are optimizations that have to be done and many other improvements. This is a first version, but it's already great that we have this working because we can test the idea of Steinheimer method, which was discussed during the lecture. So even though it's slow, but we can see that this method gives exactly the same spectrum as Langsos. So two methods are very different, but they give exactly the same spectrum. This is very interesting, and we want to check that. A few warnings. As I said, it's quite expensive. We need to use HPC. Don't even attempt to run it on the virtual machine with 2 cores. It will not work. It will crash because of disk space limit and memory and everything. And also we can try even to use parallelization over key point pools, with or without. Okay, so this is the input we do as usual. First, step 1, PW calculation. Step 2, turbo yields calculation. Now we specify calculator Steinheimer instead of Langsos. We don't have any longer keyword iter max, so we don't have those iterations which were specific to Langsos, and we don't have a restart option yet. So for the Steinheimer, we keep the Q, the coordinates of the Q vector, and then we also integrated here keywords to plot the spectrum, like broadening epsilon, units EV, starting and ending for the plot of the spectrum and increment. And we don't need to run turbo spectrum post-processing here. Since it's a different algorithm, we just do 2 steps. First PW and second turbo yields Steinheimer. Okay, before you start running the calculation, important notice, you need to do some preparatory step. We go to example 4. And let me find, so in the README file, yeah, it's actually in the README file of day 6. It's not inside of example 4, but it's general of day 6. There is a note written here. you need to do git stash, git pull, git stash apply, then close the terminal and open a new terminal and start doing this exercise for. So you did already something perhaps, but just to make sure that you did really exactly the same steps. So you need to apply, download the latest version of the material. And importantly, you need to close the terminal, because when you open a new terminal, it will apply the important changes which are done underneath. So this is important update. So once this is done, you're ready to go. In example 4, we run the PW calculation, which is taking a few seconds. Remote MPI run pw.x minus input pw. Okay, let's check. Okay, it's finished. And the final step, submitting turbo yields calculation with the Steinheimer algorithm. So we type remote SQ, remote MPI run turbo yields.x and turbo yields Steinheimer remote MPI run or remote SQ. Okay, so it's running. So note that this calculation will take two hours using 20 cores. As I told you, this is very expensive because the code is not yet optimized. So of course, this is in our plans to optimize it, make much faster, make it much more efficient. But just as a proof of concept, we can use this implementation to compare with Langsos algorithm. So I don't recommend to use a Steinheimer algorithm for production purposes. You should rather use a Langsos algorithm with turbo yields code. If you face any issues, please post your questions on Slack. But if it doesn't work, don't worry, because of course it's a very complicated example. But if you really want to make it successful and complete it successfully, then we are available on Slack to discuss. So it will take 2 hours, but let me show you the final result. This is the yield spectrum of bulk silicon computed using Langsos, the blue line, which we just discussed in example 3. So this is the converged one, the blue one, using 500 steps with extrapolation. And red dots, red circles are the one which we are computing now using Steinheimer. But you can see the two spectra are really on top of each other. But Langsos is more computationally efficient algorithm because, as Oscar said, we need to do just one Langsos calculation. It doesn't depend on frequency, so all frequencies are done in one shot. So we see we can have as accurate step as we want in frequency. While with Steinheimer, we need to do each calculation for each frequency. That's why we have the discrete number of points. We computed just 31 points because each point is a separate calculation. It's a very expensive calculation. So if you want to have a denser spectrum, like smaller distance between points, so you have more calculations to do, so more computational cost. While for Langsos, it doesn't matter. You can expand to 100 TeV or as large as you want at no cost. Just, I mean, you need to keep in mind that if you go high in energy, you you start touching excitations from the core levels. So if you want to have also excitations from the core levels, you need to make sure that your pseudopotential has those levels included. Typically core level, I mean, the idea of pseudopotentials not to have core levels, but I was referring more to semi-core levels, like deeply lined d electrons, maybe at around minus 20 electron volts, minus 30, up to 100. But if you are interested in the core level spectroscopy, which is core level EELS, so this code is not appropriate because this is for valence loss spectroscopy. We are not studying here core level spectroscopy. Okay, and the last point, convergence with respect to the K-point mesh. You can do it either with Langsos or Steinheimer, of course. So better to go for Langsos because it's way more efficient. And you see that if you use K-mesh 444, the spectrum is not smooth, not converged. But with the K-mesh 10 by 10 by 10, it's already smooth and converged. That's why we used 10 by 10 by 10. And the very last, not very last, but almost the very last point is the Plasmon dispersion. So using Turbo EELS code, you can compute EELS spectra corresponding to different wave vectors Q. For example, in this exercise, we computed spectrum for a fixed Q, which is 0.5 dot something. But you can do this calculation for different values of Q vector. For example, from 0.1 up to 1.3, you can plot them on the same figure, and you can see how it changes depending on the value of the transfer momentum Q. So you see for the small transfer momentum, you have one sharp peak. And then when Q is increasing in modulus, the peak shifts to higher energies and it broadens. So this is, it broadens because the energy of the plasmon, because this peak is the plasmon, collective excitation. So this energy is transferred. So plasmon enters in the electron hole continuum. That is to say, the energy of the plasmon is transferred to electron and hole. So this is shown here. If you take peaks, determine peaks of spectra from each spectra, and you plot them, the intensity, the peak of each spectrum as a function of Q, you should obtain something like parabolic-like. And this is called Plasmon dispersion. And as I discussed before, so this parabolic-like dispersion, this is the Plasmon dispersion, and the electron hole continuum is indicated by this dashed region. So when this Plasmon dispersion touches and then enters with continues with dashed line, so in this region, the energy of the plasmon is lost. It's transferred to the excitations of electron hole pairs. And if you're interested more in this, you can read about it in this book shown below, for example. And I think it's time to finish this hands-on. If you have any questions to any of 4 examples, please ask now. So I see one question in Slack. How does the X spectra package calculate XAS spectra with pseudopotentials? So in Quantum Espresso, there is another code which is called X spectra to study core level spectroscopy. For example, as I just mentioned, here we are discussing about valence electron excitations. But what if we're interested to study spectroscopy when we excite core electrons? This is described by XAS, X-ray absorption spectroscopy. And there is a code in Quantum Espresso to do that. We don't discuss it during this school. So the idea in X-ray absorption spectroscopy for core electron excitations, we still use pseudopotentials. But in that spectroscopy, what happens is that we're exciting core electron from, for example, from 1s level, which is very deep, to the lowest unoccupied bands, or to the Fermi level. So when we excite it, electron goes from 1s to the empty bands, but it leaves behind a core hole on the 1s level. So we need to take it into account in the calculation. But there is a problem because we're using pseudopotentials, and in pseudopotentials, we don't have core levels. So what to do? So there are different ways how to compute XAS spectra. The one which is used in quantum espresso is based on the following idea, that we need to generate special pseudopotentials that take into account the presence of the core hole. So, for example, if you take a chunk of nickel, you have study bulk nickel, and you want to measure XAS spectrum in bulk nickel. So if we have several nickel, we construct a supercell, and the core hole is localized on one of nickel atoms. So what we do, for all nickel atoms except one, we use the usual pseudopotentials. But for just one nickel where we want the core hole to sit, we use a special pseudopotential which is generated with the core hole. And with this, we do DFT calculation, and on top we use Spectra code to compute this spectroscopy. Okay, next, how different are there between chi.dat and ils.dat files resulting from turbo ils code? Yes, I haven't discussed this. Let me go to example 3 and HPC. In example 3, turbo ils code generated two files, silicon plot chi and silicon plot epsilon. So as you can guess, silicon plus epsilon contains all information about epsilon, the dielectric function and its inverse, while silicon chi contains information about chi function. Open it. We see first column is the energy, second column is the real part of chi, third column is the imaginary part of chi. So what is this chi? Is the susceptibility. This is chi. So as I said, turbo Langsos computes chi, and then in the post-processing step, we just apply this formula 1 plus 4pe squared divided by modulus of q times chi. So plot chi contains information about chi, and plot eps contains information about 1, 2, 3, 4, real imaginary part of epsilon minus 1. But typically we are not interested in chi by itself, because we cannot compare chi directly to the what is measured in experiments. We need to rescale it a bit to obtain epsilon minus 1. So that's why actually I didn't even mention about this file, but just in case you should know. There is another question on YouTube. Can the Langsos calculation be used for calculating the Plasmon spectrum of molecules? How accurate is it? The answer is yes. You can try to use turbo ils for computing plasmons in molecules. I have never worked on this, but you can try, of course, or maybe even nanoparticles, I think. But for that, it would be useful also to use probably turbo Langsos. Yeah, but I don't have experience with plasmons in molecules. Any other questions? Also to the part described by Oscar. So what does the peak mean in the IL spectra of silicon? So let's see. So this peak means, so the red spectrum is the IL spectrum, and the peak is the plasmon. I explained before why this is plasmon, because real part of epsilon is 0, or not exactly the same energy, but nearby. Yeah, so I mean, this spectrum can be compared with experimental spectra. I mean, if you are interested in the field of plasmonics, I mean, you can use this technology to determine plasmon spectra. Yes, there is also quite recent activity on acoustic plasmons. So which are plasmons which are at lower energies, not around 20 V, but really around 0, which are they have acoustic behavior, like acoustic phonons, if you want. So there are also acoustic plasmons, which are in surfaces, for example. So they behave linearly. They start from 0. I mean, not the spectrum, but the Plasmon dispersion, which is shown here. So if you plot Plasmon dispersion as a function of Q, it will be linear. It will start from 0 and will be linear for some time. So they are interesting for some technological applications, like light harvesting or the like. And also, if you study surfaces, there are also plasmons, surface plasmons. So you can also investigate them using the turbo-Ilse code. There are different types of surface plasmons, like conventional surface plasmons or acoustic surface plasmons. Yeah, there is a community working on plasmonics. Maybe it's not that large, but in case some of you is interested, probably this code can be useful for your research. I think someone is typing on Slack. You can also raise your hand. We have a couple of minutes left. So there is a question on YouTube. Is there a way to extract information about the orbitals where the transition takes place? So I guess this is about molecules, correct? Absorption spectroscopy in molecules. So if Oscar wants to answer, if not, I can answer.
Yeah, with Casita, with the Davidson, you can see the initial and virtual orbitals involved in the excitation. With the Langsos, this is not possible because we use only the occupied states.
Yes.
This is the limit of the Langsos algorithm.
Okay, if there are no other questions, maybe we can stop here. You can ask your questions on Slack.
Iurii, just one thing, thank you really much and Oscar as well from Udoganail, but this is your last lecture. So you've been giving several lectures in this school, yeah. And as usual, those resulting very clear and very well organized. So it's evident the effort behind it. So thanks Iurii, thanks a lot.
Thank you very much.
Looking forward to see you in Trieste at some point.
Yeah,
back in person.
Looking forward, really. Thank you.
Okay, so we can close the session here, and we'll be back at 2:30 CEST, so Central European Summit time for the keynote of today.